In this video, we discuss first-order linear ordinary differential equations. We'll talk about how to recognize them, how to solve them, and where the solution method comes from. So this is a first-order linear ordinary differential equation. We know it's first order because you've got a first derivative here. And we know it's linear because our y and our dy dx term have been moved to the left-hand side. All other functions have been moved to the right-hand side. And after doing that, we can see that the derivative of y is raised to the first and y itself is raised to the first. The coefficient functions depend at most on the dependent variable x, and the function on the right-hand side depends on the, I said dependent, I meant independent variable x. So if a differential equation has this form, it is a first order linear ordinary differential equation. Now, as a student, I don't want you to get confused. It looks like alphabet soup here. Generally, p of x is given to you and f of x is given to you. These are known functions. The only unknown in this equation is y, and you're trying to figure out, well, what function y that depends on x would satisfy this equation? So this is what I'm going to call standard form. Sometimes I've seen books call it general form of a first order linear ordinary differential equation. If a differential equation can be written in this form, then it is a first order linear differential equation. Well, let's look at some differential equations and see if we can recognize whether or not they're first order linear equations. So here's our first potential example. I've got 2t times y prime plus y equals negative 12t times the square root of t. Can that be written in that form? Now, I know I'm using prime notation instead of Leibniz notation. Our independent variable is t here, and our independent variable was x over there. So it looks a little different, but the question is, can I write this so that it looks like this? Well, let's see. Looks like you've got to have the derivative by itself, so I would divide out that 2t. So divide every term in the equation by 2t, and you've got y prime plus this. I think I'll write that as 1 over 2t times y equals this expression. Let's do a little algebra. The t's reduce, and you've got a negative 6t to the 1/2. Well, that's the derivative of y with respect to t plus a function of t times y equals a function of t. So yeah, that satisfies it. This is a first order linear ordinary differential equation. So it checks out. Now let's look at another one. Is that one a first order linear differential equation? I hope you said yes. If I divide everything by t squared plus 1, look what happens. Those reduce. One of those will reduce, and we end up with y prime plus a function of t times y equals this function of t. Very nice. So it's a first order linear equation. What about this one? Careful here. The dependent variable is x, the independent variable is t. So I've got the derivative of x with respect to t here, plus a function of t times x, or my function of my independent variable times my dependent variable. And then the function on the right-hand side has to depend on the independent variable only. That's an x cubed, not a t cubed. So that means this one is not a linear differential equation. Notice if our dependent variable is x and there's an x cubed in it, that would make it nonlinear. So this is not a first order linear differential equation. And the problem isn't that it's not an ODE or that it's first order. The problem is with the linearity, that x cubed makes it nonlinear. Okay, now I've used t as my independent variable in all of these cases. I've got an x as my independent variable over here. I know it makes it a little bit harder to learn, but it's very important that you get comfortable with different dependent variables and different independent variables, because when differential equations occur, we're using dependent variables that make sense. We use n for numbers of things. We use t for time. We're using these labels that make sense in context that may not match the labels that you study in math class. So I'm going to introduce you to different independent and dependent variables, and you just have to consciously try to make sense of which one is which and still match the overall pattern in order to see what methods will apply. Okay, so that's how we recognize first order differential equations. Now, actually, I'll give you one more example. Now, this turns out to be a first order linear equation. But you know what else it is? It's also separable, because I've got a function of y over here times a function of x. And if that y prime represents the derivative of y with respect to x, I could easily move all the y's to one side, move all the x's to the other, and anti-differentiate and solve the separable equation. So this is separable. But it's also linear. It's also a first order linear equation. If we distribute that cosine term, we get 2 cosine of x plus y cosine of x. And if I subtract y cosine of x from both sides, and write it in a slightly different order, so I'll have negative cosine of x times y. Then I've got my derivative of y with respect to x plus a function of x times y equals a function of x. So this is a first order linear differential equation. And the method we use for solving this, or the method we use for solving first order linear ordinary differential equations, is a method involving what's called an integrating factor. One of the Bernoullis came up with it. I'm going to show you it in just a minute. Now, for this particular differential equation, you probably want to separate the variables. It's a much, much easier method. So I just want you to see here with this example that sometimes more than one method will apply. Choose the easy one. I always recommend that you would choose the easy one, unless there's something that's particularly insightful about that method, and they're all leading to the same place. They're all leading you to the solution to the differential equation. So in this case, I would use the easier method and separate the variables rather than using an integrating factor, which we're going to talk about here. Okay, so in general, differential equations that are first order and linear are not separable. Look at, well, that one was nonlinear, but that's not separable. If I add that to the other side, I can't factor that as a function of t times a function of x. If I add this to the other side, because of that y in the expression, I wouldn't be able to factor that either. So what would end up happening is, yeah, I can't separate the variables, because if it's not factorable on the right-hand side, I can't get all the y's on one side and all the t's on the other. And then this one is also not separable. So the question is, what do we do? If we're here with something that looks like this, and we're trying to figure out what y is as a function of x, what could we possibly do to get y by itself? Now, if you're taking this class for the first time, you might be thinking, well, let's just take an antiderivative. I've got a derivative here. Well, just take the antiderivative of both sides, like we did with the separable ones. And I love the way you're thinking, if you're thinking that, because yes, antiderivatives do undo derivatives, and that would get us closer to the answer. But if I took the antiderivative of this side, I'd have the antiderivative of the derivative, which would give me y, plus an antiderivative of a product, which I might be able to rewrite using integration by parts, but one of the unknown functions in that integral will be the the y, that unknown function y. And that would be a little bit of a problem. And then the integral of f of x, provided it's a nice function, we'll be able to take the antiderivative. So I guess my point is, if we tried to use anti-differentiation to get rid of this differentiation, we'd end up with the integral of a function times our unknown function y. So getting rid of the derivative would just introduce an integral of y, or an integral involving y, and that really wouldn't help us. So we have to do something else. Well, there are a lot of things that these Bernoulli guys came up with, their whole families in math and science and studying lots of things. And there's all kinds of drama and intrigue if you read like history of math and science about things in their family. I have not done the research and figured out which of the Bernoullis came up with the method that I'm about to teach you right now. But one of these guys in this very mathematical family said, what if I take this differential equation and multiply by just the right thing? Let's look at that. I've got the derivative of y, and then I've got plus something that has a y in it. Well, wouldn't you see something like that from a product rule? Remember, derivative of a product is the derivative of the first times the second plus the derivative of the second times the first. Like, couldn't that function be like y? So I'd have a y prime and a y, so that it looks kind of like that. He said, what if I multiplied by just the right thing so that this left-hand side was exactly what I would get from the product rule? So let's see. Let's call the unknown function that we're multiplying by mu of x. That's standard notation. And let's take this differential equation in standard form and multiply by mu of x. Now remember, these functions p and f are going to be known. So in this case, p was 1 over 2t, f was that negative 6t to the 1/2. So these are given to you. Even though it looks like they're not given to you right now, it's just because we're talking about this in abstract. We're going to make it more concrete when we do examples in a little bit. So I want to multiply by mu of x. And my goal in multiplying by mu of x is to choose mu of x such that this is the derivative with respect to x of y times that function mu of x. Mu of x is called an integrating factor. The question is, what would mu have to be for this to work, for this left-hand side to actually give me this? Well, that's pretty easy. In order to figure out what mu would have to be, I can just expand this. According to the product rule, if this is my first function and this is my second function, I should get the derivative of the first times the second plus the derivative of the second function times the first, and the first in this case is y. And we still have that f of x mu of x over here. I need these all to be the same thing. Like, I need this to be equal to this, and it is by the product rule, and I need this to be equal to that. So the question is, well then, what does mu of x have to be? Well, these guys already match. So I've got mu times y prime right there and mu times y prime right there. I'm good. The only part that doesn't match is this part. And actually, the y's match. Now I'm here. In order to figure out what mu would have to be, so that multiplying by mu would make this left-hand side the derivative of a product, y times mu of x. Then I just have to solve this simple differential equation. The only way that this is going to be equal to this is if mu prime is equal to mu times p of x. And I'm just dropping the dependence on x, but we remember that it's there. Or if you prefer, you can put that dependence on x back. Makes it a little easier to see what's going on. And I might even drop the dependence on x on this one, but not that one. Let's separate the variables. This is a separable differential equation. We'll divide both sides by mu, multiply both sides by dx, and then antidifferentiate. Oops, excuse me. The antiderivative of 1 over mu with respect to mu is natural log of the absolute value of mu. And on this side, well, it depends on what p of x is, so I just need to leave that as the integral of p of x. To get mu by itself, I will exponentiate. So I have the absolute value of mu is e to this power. And we're going to multiply by mu later. So if mu happens to be positive or negative, well, I'm going to end up multiplying everything by -1 anyway, so it's not going to matter. So that absolute value actually isn't necessary in this case. So let's let mu of x equal this. That's our integrating factor. It turns out if you multiply this equation, well, this equation right here, by e to the integral of p of x power, the left-hand side becomes the derivative of y times that integrating factor. And that's great. You might think, well, why on earth would I care about that? It's great because if I have the derivative of y times this equals this, I'm 2 steps from getting y by itself. To get rid of the derivative, I antidifferentiate. To get rid of the mu that's multiplying, I just divide. So I'm just a couple of steps away from getting y by itself. If I can write this left-hand side as the derivative of this product. So that's what one of these Bernoulli guys came up with. That's what he thought of when he came up with this method for solving first-order linear equations. He said, multiply by this, and then you're basically 2-3 steps away from getting y by itself. Okay, so let's look at the method in abstract, and then we will look at a specific example. So here's the method. We start with dy dx plus p of x times y equals f of x. Or if we don't start with that, that's our first step. We're going to write the differential equation in standard form. And standard form is just this form that I've given you right here. Then you're going to identify p, and compute its antiderivative. So I'll say you're going to compute this. Then you're going to let mu equals e to that power be your integrating factor. I'm just going to abbreviate that with IF. So normally we calculate that. And then after we've computed mu, then we multiply both sides of the equation by mu. So you've got this differential equation. I'm just going to write it down. And you're going to multiply everything by e to this power, and e to this power, and e to this power. Now, if you've done everything correctly, so your anti-differentiation is correct, e to that power is correct. Usually there's a little bit of simplification there. If you've done everything correctly, then the left-hand side will be the derivative with respect to x or your independent variable of your dependent variable times your integrating factor. So you should check. You should use the product rule to check. If we've done everything correctly, this should be the derivative with respect to x of y times the integrating factor. And you've still got your function times e to that power over here. Okay, now let's check this out. According to the product rule, we get the derivative of a product is the derivative of the first times the second. That's there, good. Plus the derivative of the second times the first. Well, the y is there. The question is, what is the derivative of e to the integral of p of x power? Well, the derivative of e to some power is e to that power times the derivative of the inside. And what's the derivative of the antiderivative? I hope you said the original function, because if you did, you're right. Anti-differentiation and derivatives, differentiation, undo each other. And so we get p back. So this works. This gets us this. And even though this looks complicated, you're going to know what p is. So this is actually going to be a function. And you're going to know what f is. That'll be a function too. You're just trying to get y by itself here. So now that you've recognized the left-hand side as the derivative of that product, to get rid of that derivative, you're going to anti-differentiate both sides. So you're taking the antiderivative of the derivative of y times the integrating factor with respect to x. Don't be distracted by that. I almost just want to write an IF. It's just the integrating factor. And make sure that if you're anti-differentiating the left-hand side, you do the same thing on the right-hand side. So you've got that. The antiderivative of the derivative is the original function, so you get your product back. I'm just going to write IF now. And so you've got this here. That you're going to have to simplify and anti-differentiate. And then if you want to get y by itself, what do? After you anti-differentiate to get rid of the derivative, you're going to divide by the integrating factor to isolate y. Now, of course, the integrating factor is a function of x. You can't just take this function of x that's inside an integral and divide by a function that's outside an integral. That's not how it works. You actually have to do this computation first, then anti-differentiate, and then divide. Now you're going to get a constant of integration from this. Make sure you divide that constant of integration by the integrating factor as well. And then you should be good to go. Okay, so that's the method in abstract. Let's do it. Let's do one concrete example. And then I think I will make another video with another concrete example. So let's look at this guy. I've got 2t times y prime plus y equals 12t times the square root of t. Oops, it's minus equals negative 12t times the square root of t. And let's put an initial condition on there so we can practice finding the value of our constant. Okay. I've got a y prime to the first times a function of t plus a function that's just a 1, depends at most on t, times y to the first, and then a function of t over here. So this is linear. First thing to do is to write it in standard form. So let's divide everything by 2t. And we're here, the t's reduce. I'll call that t to the 1/2. Then you identify p, that's the function in front of the y once you're in standard form. And then anti-differentiate it. So that's 1/2 times the integral of 1 over t dt. That's 1/2 times natural log of the absolute value of t plus c. And then we're going to define our integrating factor. People tend to use mu for it. I just usually write IF or e to that power. So I've got e to the 1/2 natural log of the absolute value of t plus c power. Careful here. We want to simplify this as much as possible, and we can because of the exponential and the log, but you have to be very careful about your algebra here. Now remember, if I've got a sum of two terms in an exponent, it's like using this rule backwards. I've got two of those, I can rewrite that as a product. I can write it as the base to that first power times the base to the second power. In algebra class, we normally went from here to here, but now we're gonna go backwards. So this is e to the c times e to this power. And that e to the c is just a different c. So I'm just gonna call it c1. Now for this guy, in order to simplify the e and the log, I can't have that 1/2 out front. So I've got to rewrite that logarithmic expression. Remember how this works from your log properties in pre-calculus or college algebra. If you've got a number out front, you can bring that inside. That's actually natural log of a to the n. So this is actually a natural log of t to the 1/2, or if you prefer, the square root of t, that's totally fine and legal. Actually, it's for the absolute value of t there. And the e and the log undo each other. And I think I'm just going to call that c1 times the square root of t for t greater than 0. It would be the square root of negative t if t were less than 0. Since t equals 1 is part of our solution curve, and we're going to have an issue if t equals 0. We can't take the natural log of 0. I'm going to choose this implied domain of t being positive, because if I'm splitting this into negative infinity to 0 and 0 to infinity, if I'm splitting the real line in that way, I want to choose the interval that includes my initial condition, that initial t value, t equals 1. So I'm going to choose for t to be positive. Then the absolute value of t is just t, and we're here. So our integrating factor is this after simplifying. That's what it ended up being. Now, you might be thinking, well, what was I doing again? Or we take this differential equation in this form and we multiply by the integrating factor. So we had y prime, or I prefer Leibniz notation, dy dt, plus 1/2t times y equals -6 times t to the 1/2. And we're multiplying everything by a constant times the square root of t. Constant times the square root of t. Do you see that multiplying by that constant didn't really do anything to our differential equation? Like, now I've just got this arbitrary constant everywhere. You could divide it out. Let's divide everything by c1 and that's gone. But instead of doing that every time, let's go back and figure out where that c1 came from. Well, remember that c1 is here, and it came from here, and that c1 came from this e to the c, and the e to the c came from that e to the c, and that c came from here. It came from this constant of integration. I don't really need that, because all that did was multiply by a constant, and I'm going to divide it out anyway. So we can choose for this c to be 0, and it's not going to affect anything. And we're going to, if that's 0, this is e to the c, which is 1. That makes that a 1 and that a 1. And now our integrating factor would just be square root of t. Okay, so we've multiplied by the integrating factor square root of t, which is the same as t to the 1/2. And if that's t to the 1/2 and there's a t to the first in the denominator, that'll simplify that way. And t to the 1/2 times t to the 1/2, you add the exponents and you get that. So you multiply by the integrating factor and simplify. And then if you've done everything correctly, the left-hand side should be the derivative of your dependent variable y times the integrating factor. If you've done everything correctly, that should be true. So I'm going to say recognize that the left-hand side is the derivative with respect to your independent variable, which happens to be t, of y times your integrating factor. And at this point, because we have to do all these little algebraic things in order to simplify with our exponent properties and our log properties, it's always a good idea to check. Well, let's check using the product rule. The derivative of the first times the second would be this. And then the question is, what's the derivative of the second? Well, that's 1/2 times t to the negative 1/2 by the power rule, right? And 1/2 times t to the negative 1/2 is the same as this. So I can put that t to the negative 1/2, I can rewrite it with a t to the 1/2 in the denominator. So the derivative of this product is this. It's derivative of the first times second, plus the derivative of the second, which is there, times the first, equals that. And that's great, because that means I'm 2 steps away from getting y by itself. Say thank you, Mr. Bernoulli. My advisor in graduate school, he says, something that we teach our students in an hour, somebody spent 1,000 hours developing. So thank you, Mr. Bernoulli, for the 1,000 hours you spent, perhaps, developing this method so that we don't have to. We can stand on the shoulders of giants and learn from the results that other people came up with. So we're here, we're trying to get to y, and I've got the derivative of this product involving y equals this function of t. In order to get rid of the derivative, we anti-differentiate. Both sides with respect to t, and the antiderivative of the derivative is the original function. The antiderivative of 6t to the first, bring that negative 6 down, add 1 to the exponent, divide by the new exponent, add a constant. We already used c and c1, let's use c2. Of course, we can simplify that. Oops, it's multiplication, not equals. And the last thing to do to get y by itself is just to divide by that t to the 1/2. And you could divide everything by t to the 1/2 if you want to. And this will work on the interval from 0 to infinity. We can't divide by 0. And I'm choosing the interval 0 to infinity because of the choice that I made here, and I made that choice here because of that initial condition. Now, if I want to find the value of c that actually makes this work, then we have to use the initial condition. But let's see, what did we do? We anti-differentiated, and we divided by the integrating factor to isolate y. And then we stated the general solution. Turns out these are going to give us general solutions, the family of solutions that contains them all. And we stated a maximal interval of existence.